Hello to everyone, I am Luca Ciccone, and the work that I'm going to present is called Fair Termination of Binary Sessions. So first of all, let's see what binary sessions are. A session is a communication channel that connects a couple of processes, where each of them has an endpoint of the session. Session types are types that are associated to the endpoints and tell how they are going to be used by the processes. When we assign types to the endpoints of the same session, we usually consider dual types. And here, in this very first example, we can see a pair of processes, P and Q, that communicate using session X. Here, for example, we can see that P is going to use the endpoint X to send a label A, then to receive a label B, and then to send a signal to terminate the session. Q is going to use X in a dual way, such that it will receive a label A, then it will send a label B, and at last, it will terminate the session. Actually, when we deal with session types, we also consider branching points. And here we can see the two main constructs. The first one is called choice, and it models a process that can choose to send the label A and continue according to T, or send the label B and continue according to S. On the other hand, the second construct is called branch, and it is the dual of the previous one. It models a process that can receive a label A or a label B and continue according to T or S respectively. Coming to the properties that we can prove using these basic notions, if we consider dual endpoints of the same session and we consider only finite types, we can state that all interactions eventually terminate, which is a liveness property. Actually, this is not the case if we move to infinite types. In this case, we are only able to state that interactions will never get stuck, which is a safety property. Actually, this is not bad, but we would like to prove some stronger property. So our aim was to develop a type system for enforcing fair termination. Fair termination means that all fair interactions terminate. That is, infinite interactions are considered unfair because they violate some fairness assumption. And in this context, the assumption that we made is called strong fairness, which states that every action that is infinitely often enabled is infinitely often performed. Notice that we are dealing with a liveness property again. Now I would like to informally show the steps that we made to develop our type system. And so first of all, we started from the fact that processes may behave differently with respect to the protocols that they implement. And this discrepancy between the actual and expected behavior is usually modeled with a subtyping relation, which has been originally introduced by Gay and Hall. This subtyping relation is unfair in the sense that it is studied to preserve safety but not liveness. And so we relied on fair subtyping, which is a liveness-preserving refinement of the original subtyping relation. Then we noticed that fair subtyping must be used in a very controlled way, because, for example, infinite applications of a subsumption rule, for example, in the typing of a recursive process, may lead to an application of the unfair subtyping. So the type system must take into account all these problems, and in this case, it must avoid too many applications of the subsumption rule. To conclude, the soundness theorem that we managed to prove is the following. If the process P is well typed, then P is fairly terminating, which means that all sessions in P eventually terminate. Thank you for the attention.